All right, we're just about done with section 2.2, part 2, but we just have one more example to cover, and this example is the one about parallel and perpendicular lines, which is one of our goals for this section. All right, we've just had a discussion over the three forms of a line, and they should begin to be a little bit more familiar to us. All right, here are three examples of those forms: point slope, standard, and slope intercept form. Now you already have these things written down in your notes, hopefully, from that study guide we started at the very beginning of the lesson. We had all three of these forms written down as well as slope formula. All right, so the one you're most familiar with would be slope intercept form, y equals mx plus b. This one is the most useful for graphing purposes. You're already excellent at finding our y-intercept and then moving based on our slope, the rise over the run. But we've also been discussing standard form and how it can be useful, particularly when we're solving for the x and the y-intercepts. Now this particular standard form, the way it's written, if we were to graph this line, it would be easiest in this case to solve for y by subtracting 3x to both sides and graphing in slope-intercept form. So we can kind of see how it's easy to relate one to the other. We also discussed in class how, let's say, if this c value here is evenly divisible by a and b, then it's easiest to graph standard form by plotting the x and y intercepts. Now, if you weren't here in class yesterday, then that idea still may be a little bit fuzzy to you, and we'll recover that type of example when we go over our homework next class. But again, standard form is useful, particularly when the c value is evenly divisible by the coefficients a and b, and in that case, we would be graphing the x and the y intercepts, and that's the most efficient way to graph that line. Finally, in the previous lesson, from the previous video, we talked about point slope form and how it can be useful if we are given a slope and a point first. Once again, it's easy to transform point slope into standard or slope intercept form for that matter by distributing here and then solving for y or moving the x and y on the same side depending on which one that we're trying to accomplish. So that's kind of a goal for this section, is being able to fluidly transfer from one form to another, and for you to recognize really that they are all kind of discussing the same topic, just in three different ways. All right, so our last thing to talk about in section 2.2 are four special cases: horizontal, vertical, perpendicular, and parallel. Now, these four lines have properties that you may just have to memorize. They do make sense logically, but if you're finding trouble remembering which one is which, then you may just want to add these things to your study guide that we were creating and memorize it for a test or quiz over this material. All right, the book starts us off with horizontal lines. Now, horizontal lines, two things I want you to notice. First, their slope is automatically 0. And that should make sense to us because we see, if we're talking about this line here, it really has risen none, right? There's no arc to it, there's no slant to it. And so if we're thinking about slope formula, which is y2 minus y1 on the numerator, then if our y values are the same, which they are here, that numerator would be 0. And so the slope is just going to be automatically 0 for anything that we see as horizontal. The second thing I want you to recognize is that the equation always comes in a certain form, which is y equals a constant value. Here they're symbolizing that with b, but they mean it's a number of some kind. So an example here would be y equals 3 or y equals -4. Graphing these things is very easy. If we were to graph the line y equals 3, for instance, all we would need to do is find 3 on the y-axis, mark that point, and then draw a horizontal line. And that's it. Some students find horizontal and vertical lines difficult to memorize because there's a little bit of a disconnect between the y and the x representing horizontal versus vertical. So I'll show you what I mean. With a vertical line, it takes this form x equals c, meaning a constant here again. And so an example of a vertical line would be something like x equals -2 or x equals 4, x equals any number. Now similar to the horizontal line, the slope here is a little unconventional. Here they mean that m is undefined. And again, we get this from slope formula. If we're talking about a vertical line, all the points here have the same x value, which means in slope formula, the x2 minus the x1 on the denominator, those would be the same number. And so if we had, let's say, 2x coordinates of 2, then 2 minus 2 would give us 0, and we'd be dividing by 0. And that's why they're showing us m is undefined in this case. All right, so what I was talking about before with the reason why some students find this difficult is because we're used to thinking of x values as corresponding to a horizontal movement, y values corresponding to a vertical movement, and so some students see the fact that the x line is a vertical line, the y line is a horizontal line, as a little bit confusing, but it does make sense, right? All these points on this line have the same y coordinate. All the points on this line have the same x coordinate. So there is a logic behind why they look the way they look, but again, you may just have to memorize it if you're feeling a little confused by what's going on here. All right, so that's horizontal and vertical lines. The next two lines that we're going to talk about are perpendicular and parallel. And if you remember from the beginning of the previous lesson, I said that if we're dealing with parallel and perpendicular lines, then we're talking about some sort of relationship between slopes. And so you may remember from Algebra 1 that perpendicular lines do have a related slope. In this picture, they're showing us perpendicular lines, and they're symbolizing that with this little wedge marking here, which we remember from geometry to mean perpendicular. So not only can we tell that these lines are perpendicular by the wedge marking, but we can also solve for that algebraically. Now the main piece of information that you need in order to solve for perpendicular lines is this, that one slope is the negative reciprocal of the other one. So for example, if we had a line that had 2 as its slope, then we could easily solve for the perpendicular slope because it would be the negative reciprocal. Now the negative reciprocal of 2 would be -1/2. And so we can easily tell whether or not lines are perpendicular by simply comparing their slopes. Similarly, if we had one slope that was, let's say, 4/9, then the opposite reciprocal of that slope would be -9/4. And that would give us the perpendicular slope to that original line. All right, similarly for parallel lines, once again we're comparing slopes. The main thing that you need to know from here is that the slopes are the same. And that should make sense to us because if we're talking about parallel lines, then they rise and they run the same way. So it's like we're saying they share a rise and a run, or they share a slope. Also notice this notation down here, they say that B1 cannot equal B2. Here they're referring to their y-intercepts. The reason why they say this is because if they shared a slope and they shared a y-intercept, we really would be talking about the same line. And so in order to find two parallel lines that are different, we have to make sure that they share a slope, but that they do not share a y-intercept. Because again, if they shared a y-intercept, we would be talking about the same line, not two distinct parallel lines. All right, so to sum up here, horizontal is y equals a value, the slope is 0, vertical, the slope is undefined, and we have the form x equals some sort of value. Perpendicular, the slopes are negative reciprocals, and parallel, the slopes are the same. All right, last example in section 2.2. They give us this problem here. Find the equation of the line through each point, so they're going to give us several, that is also perpendicular to the line y equals 3/4 x plus 2. Now, if we were trying to find parallel instead of perpendicular, it would be pretty easy. We would just use this same slope here, 3/4. But here they're talking about perpendicular, which is the harder of the two. And so the first thing we do is we look at this slope here, and we need to find the opposite reciprocal. So the slope in this case is 3/4. The opposite reciprocal is going to be negative 4/3, which they show us here in this example. Now they're using that kind of confusing notation with the 1/over nonsense. You don't really need that here. All you need is to figure out the opposite reciprocal. You should remember this from section 1.1. It's negative 4/3. We get it. All right. This point that they're giving us in part A just so happens to be an important point. If the x-coordinate is 0, we know automatically that we have here the y-intercept. And we know that because for a y-intercept, the x-coordinate is always 0. So if we have the slope and we have the y-intercept, then very easily we can use slope-intercept form in order to get our answer. All we need is to plug in our m, plug in our y-intercept, and we're done. So they show a slope-intercept form, we plug in our values, and that's it in this particular case. For part B here, they're giving us a different point. It's not a significant y-intercept like we had in part A. There are two ways of handling this. First of all, we're going to be using the same slope that we used in part A because, again, we're solving for a perpendicular line, and again, the slope has to be the negative reciprocal. So since we're using the same slope, really the problem that we're doing isn't very difficult because we already have the slope and now we have a point. The easiest form of a line to use in this particular case, if we have a slope and if we have a point, would be point-slope form. Now the book is going to show us a slightly different way of solving for this using slope-intercept form, but you're welcome to use either method. If you were going to use point-slope form, really arguably a very efficient way of solving this problem, we would take this slope that we see here that we solved for, plug it into the m, and then use these values here for x1 and y1. So the answer in that case would be y minus 1 equals negative 4/3 parentheses x minus 6. From there, we could transform that into slope-intercept form if we really wanted to, but since this problem says just write an equation, it doesn't specify the form, we could use either one. Now the book here is going to use slope-intercept form, which is something you're also welcome to try. And this is the method I personally used when I was in high school, but it's up to you, whatever you think. So we're going to plug in our slope into the m, and since these values here are sample solutions of y and x, we can plug them into where we see x and y in slope-intercept form. Once we do that, we're solving for b. So we'll simplify here by reducing. 6 divided by 3 gives us 2. 2 times negative 4 gives us negative 8. And then we'll solve for b, which gives us 9. So our final answer here is y equals negative 4/3 x plus 9. All right, I want you to try A, B, and C. Feel free to pause the video before you look at the answers. And here are your answers.